Welcome back to ScienceClic. Today, quarks. Elementary particles are the smallest constituents of matter. They cannot be divided into smaller objects. They are the basis of everything we know, from the most microscopic structures to the largest galaxies. Quarks are one type of elementary particles. They can be subdivided into 6 different types: the up, down, charm, strange, top, and bottom quarks. Quarks have 3 particularly interesting characteristics. First of all, their mass. Some quarks are heavy, and others are lighter. The up and down quarks are the lightest of all. They therefore require relatively little energy to create and are very stable. For this reason, they are the most common quarks in the universe. By gathering in groups of 3, the up and down quarks notably form protons and neutrons, which are the basis of all atoms. In terms of mass, the charm and strange quarks come next, being several dozen times heavier. Finally, the top and bottom quarks are the heaviest of all. The top quark in particular is more than 70,000 times more massive than the up quark. Because of their very large mass, these 4 quarks are much rarer than the up and down quarks. They require a huge amount of energy to create and are very unstable. They are mainly found in particle colliders, where we create them voluntarily by means of very energetic reactions with the aim of studying them. The second interesting characteristic of quarks is their electric charge. In the universe, all other elementary particles have a whole electric charge, which can be either 0, no charge, 1 positive charge, or -1 negative charge. Quarks, however, only have a fractional electric charge, one that corresponds to a fraction of a whole charge. The up, charm, and top quarks only carry 2/3 of a positive charge, and the down, strange, and bottom quarks carry only 1/3 of a negative charge. This very peculiar characteristic of holding only a fraction of a charge makes quarks unique among elementary particles. That said, although quarks only have a fraction of a charge on their own, they always gather together so as to form groups whose total electric charge is whole. In the case of the proton, for example, which is made up of 2 up quarks and 1 down quark, the different fractions of charges carried by the 3 quarks add up to form 1 total positive charge. In the case of the neutron, there are 2 down quarks and 1 up quark, which compensate each other to form a 0 total charge. In our universe, there exists for each elementary particle a sort of twin particle, which has the same mass but an opposite electric charge. These are called antiparticles. They are the basis of antimatter. Quarks do not escape this rule, and there are therefore 6 antiquarks whose electric charge is opposite to standard quarks. In nature, they can be found in pairs with their respective quarks, thus forming groups whose total electric charge is 0. Finally, aside from their mass and electric charge, the most intriguing characteristic of quarks is something called their color charge. Color charge is another type of charge that all quarks carry. Unlike the electric charge, which is a single value, either positive or negative, there are 3 types of color charge, which physicists have named red, green, and blue. These color charges have absolutely nothing to do with the visual notion of color. The terms red, green, and blue are only names which have been chosen arbitrarily to designate the 3 charges. In the universe, each quark has a color charge, either red, green, or blue. Antiquarks, as we have seen, carry opposite charges: anti-red, anti-green, and anti-blue. Just like the electric charge, if we group several quarks together, their color charges add up. If we group together a red quark, a green quark, and a blue quark, the whole has a total white charge, that is to say, neutral. Likewise, if we group a quark with an anti-quark of opposite color, for instance red and anti-red, the couple will also have a total white charge. In nature, quarks always group together to form combinations with a total white charge. For instance, in a proton, the three quarks must be red, green, and blue so that the total charge is white. The same goes for a neutron, as it also does for a quark-antiquark couple. Another interesting feature of color charge is that it can change over time. For example, imagine a quark with a red charge. Due to quantum phenomena, there is a probability that the quark suddenly changes color, for instance becoming blue. By turning blue, the quark loses its red charge. This charge escapes in the form of a brand new particle, separate from the quark, which we call a gluon. The gluon carries with it the red charge as well as an anti-blue charge, to compensate for the blue charge which has just appeared in the quark. More generally, gluons always carry a standard color charge, red, green, or blue, as well as an anti-charge, anti-red, anti-green, or anti-blue. Let's imagine that nearby there is a second quark, which is already blue. If it receives and absorbs this gluon, it will change color as well. More specifically, it will lose its blue charge and receive the red charge of the gluon. During this process, things happen as if the red quark had swapped color with the blue quark. In the universe, these gluon exchanges are frequent, and quarks are constantly swapping colors. This interaction at a distance holds quarks together, a bit as if they were connected by an elastic band. If we try to drag one of the quarks away, due to complex phenomena, the quarks will start attracting each other more and more strongly, somewhat like the rubber band which becomes more and more tense when trying to stretch it. This powerful effect is called the strong interaction. It is one of the four fundamental interactions ruling the universe. The strong interaction ensures that quarks stay together, guaranteeing, for instance, the cohesion of protons and neutrons. Finally, an important consequence of the strong interaction is that it is experimentally impossible to observe a quark alone. To understand, let's imagine that we decide to isolate one of the three quarks from a proton. When we pull on this quark to separate it from the others, the attraction becomes stronger and stronger. But if we pull hard enough on the quark, it is still possible to knock it out of the proton. However, the moment we manage to isolate it, everything happens as if we had broken the elastic band that linked it to the other quarks. The energy of the bond is suddenly released and gets converted into matter, forming a brand new quark-antiquark couple. In the end, we have succeeded in removing the quark from the proton, but it is still not isolated because it is now paired with an antiquark. This phenomenon, which prevents quarks from existing on their own, is called color confinement. It has the effect of keeping protons and neutrons linked together, thus ensuring the cohesion of the nuclei and therefore stabilizing most of the matter that makes up the universe.